In the previous video, we discussed how multiple solar cells are connected to make a module. Now we will look at the characteristic IV curve of such a PV module. In this video, we will start with the IV curve or current voltage curve of a single solar cell. We will then build up an ideal module and look at its IV curve. Finally, we will discuss the various mismatch effects that affect a real module. Let's begin with the parameters that characterize a solar cell. Note that the vertical axis represents the current, while the horizontal axis represents the cell voltage. This black curve indicates the current voltage curve of an illuminated solar cell, while the red curve depicts the current voltage curve in the dark. From this plot, we can discern the characteristic parameters of a solar cell, such as the open circuit voltage VOC, highlighted here in blue. The short circuit current ISC is indicated in orange. The maximum power point, where the product of the current and voltage is maximal, is indicated by the green arrow. With these parameters, we can determine the fill factor. The fill factor is the ratio between the maximum power generated by a solar cell and the product of the VOC and the ISC. Graphically, the fill factor is equal to the ratio between the yellow dashed area and the blue area. Finally, the efficiency of a solar cell is equal to the ratio between the output and input power. In practice, this means that the efficiency is equal to the maximum power output divided by the incident power. The incident power in this case is equal to the product of the irradiance, which is generally equal to 1000 watt per square meters according to the standard test conditions, and the cell area AM. To see how the IV curve of a module is different from that of a single cell, let's first look at the IV curve of an ideal module. For this module, we assume that all the interconnected solar cells have identical electrical characteristics and all experience the same insolation and temperature. All cells will be therefore operating at exactly the same current and voltage. Consequently, the IV curve of the PV module has the same shape as that of a single cell. The IV relation of an ideal module is described by this equation, which is derived from the illuminated diode equation. The voltage and current of the module are indicated by IT and VT respectively. The number of parallel connected solar cells is indicated by capital M, while the number of cells in series is indicated by capital letter N. The lowercase n is called the single cell ideality factor, which is here justified having assumed that all cells in the module are identical and operating under the same illumination and temperature conditions. ISC is the short circuit current of a single solar cell, and I0 is the saturation current. Ideally, the total current of a PV module would be the product of the current of an individual cell and the number of cells in parallel. And the total voltage would be the voltage of an individual cell multiplied by the number of cells in series. However, as you can imagine, this is not the case in reality. We have to account for different loss mechanisms in a solar cell and in so-called cell-to-module losses. These losses change the dashed ideal current voltage characteristic to the more realistic red one. The loss is visible here at the maximum power point, which is a bit lower than the theoretical one. This decrease in fill factor is caused by the shunt and series resistance of the module. Indeed, the slope on the left of the maximum power point is due to a decreased shunt resistance that occurs during the fabrication. The greater the shunt resistance, the smaller the slope, and therefore the better the performance of the module. At the right side of the maximum power point, the cell experiences an extra slope due to an increased series resistance. This increased series resistance occurs when the solar cells are interconnected with metallic tabs. Now, it is important to note that there are 4 quadrants in this IV coordinate system. When either the voltage or current is negative, then the resulting power is also negative. This means that the solar module is dissipating power in the form of heat. For example, in case of partial shading, the solar cell operates in the reverse voltage region. At some point in this region, the reverse biased solar cell experiences a very high current that may cause a breakdown of the junction. Only when both quantities are positive, the module generates power that can be delivered to the load. We have now discussed the IV behavior of a single solar cell, an ideal PV module and a non-ideal PV module. In the next video, we will continue our discussion of the IV curve of interconnected cells.